All right, so this is the last section of the semester. Cue the fireworks. So we're going to use what we talked about last time, finding the correlation coefficient. And what we're going to do is we're going to learn how to find a very specific line of best fit called the least squares regression line. Okay. So basically, if you have a scatter plot and it's not in a perfect line, this will kind of estimate what a linear equation of best fit could be so that you can make judgments and use that formula to kind of predict future data. All right, so remember back in algebra, we looked at equations of lines quite a bit, right? So the slope-intercept form is y equals mx plus b, okay, where m is the slope and b is the y-intercept. And so the least squares regression format is going to look kind of close to this, but typically they write things opposite. So just kind of be aware of that. So the regression line equation, it doesn't really matter what order you write the terms in, and so it will usually look like this. It is y hat equals b sub 0 plus b sub 1 times x. Okay. Notice this really is the same format as this, we just use different letters. B sub 1 is the slope, B sub 0 is the y-intercept, and then we still have a y and an x. It's just that this one has a little hat on it. Because you can find the slope by doing r times the standard deviation of the y's over the x's. Remember, slope is always change in y over change in x, so this is kind of a version of that. Standard deviation of y over x, and then times that correlation coefficient we talked about in 4.1. And then b sub 0 is always equal to the y value minus that b sub 1 you just found in the other value. Sorry, the y average minus the b sub 1 times the x average. So this is a times dot here. Okay. So in other words, once you have r, you'll already have these two, and you can fully figure out what the equation of the line is. It's just that these are going to be more specific than your traditional algebra mx plus b. We're going to probably have decimals here because it's going to be based on real data that does not fall in line perfectly. So once you have a linear equation, then you can predict future y values based on any given x value. Okay, so this kind of prediction method is actually used in real life data all the time. So maybe you've collected data from a whole lot of sources, but you want to use that data in order to predict what future values you're going to get. Okay, so I want you to compute the least squares regression line for predicting y from x given the following values. So if you have all these values, this doesn't take that long. So let's say that these are the values that someone already figured out for you. Okay, so notice this is a negative r, which means as one of the values go up, the other one's going to go down. Okay, That automatically, by the way, means that we're going to have a negative slope, right? But a rate of change is always what the slope is. And so if one's going up when the other one's going down, the slope is going to be negative. So we're going to use this. So let's use our formula. So b sub 1 equals r times the standard deviation of the y over the standard deviation of the x. So it's going to be r times 1.9 over 1.2. Okay. And this is going to go to 4 decimal places in the end, which means in the intermediate steps we're going to use 8 decimal places. A good rule of thumb, remember, is if you want 4 in the final answer, use double that. Okay. If you want 3 in the final answer, use 6. If you want 4, then you want to use 8. Okay, b sub 0, the formula for that is the average of the y's minus the b sub 1 you just found times the average of the x's. So it's going to look like 30.4 minus, and then that big old long decimal, and then times 8.1. So b sub 0 works out to be about 41.3012, 4997 if we take it out to 8 decimal places. Okay, and then always this is just going to be your slope. And this is going to be your y-intercept. Okay, so your b sub 1 is your slope, your b sub 0 is your y-intercept. So when I want to look for the equation for y, it's, remember, in the other order. So we actually list the y-intercept first and then the slope. On Connect Math, I don't think it'll count you wrong if you list this term first, but this term has to go with the x. You can't swap the location of the numbers without moving the x too. So the slope is negative 1.3458. The y-intercept is about 41.3012. Okay, so let's go ahead and pull back in the example we did from 4.1. So refer to example 4 in sections 4.1 notes. Okay, so you don't have to flip back there if you don't want to, but these are the values that we got. Remember, it was the price of eggs versus the price of milk problem. Okay, so that's a summary of what we got back when we looked at that. So let me just look real quick and make sure I wrote down all those numbers right. You want to do some quick double takes to make sure that you don't write something down wrong. I think the R was actually 0.845, right? Yeah. So that's why I wanted to make sure before we proceed. All right, so using those values, the first thing I want you to do is I want you to compute the least squares regression line for predicting the price of milk from the price of eggs. Now again, we're still not saying that one causes the other, but we're just saying that because they tend to move together or go up or down together, that maybe if we know the price of eggs, we can predict what the price of milk would be. All right, so first we'll find b sub 1. Okay, so remember that is r times s sub y over s sub x. So actually, let's go back up here. Let's take the full R value from before. I know that I rounded it, but the full R value without it being rounded is probably more useful here because we don't want to round R prematurely and then have to use it later. Okay, so if you look back at example 4 in section 4.1, we actually could have been more specific. We just ended up rounding it to 3 decimal places because that was our final answer. So, but this is actually what the answer is. Okay, or what the answer is, just 6 decimal places. All right, so this is going to be approximately, since R is not exact anyway. And we're going to multiply that by this fraction. And we're going to get 0.39906,909. Okay, I only had 6 decimal places for the last problem, but notice I used 6 for all of these, but I'm still going to go ahead and use 8 here just to make it a little bit more accurate, because my final answer is still going to have 4 decimal places. So B sub 0, remember, is y average minus the B sub 1 you just got times the x average. So it's going to be about 3.4925 minus that B value we just got, and then times 1.8375. Okay, so this comes out to be 2.75921055. Actually, I guess I included 1 too many decimal places there, but that's all right. That was all that was on my screen, so you could probably cut that down, because in the end, we really just are going to round it anyway. So y bar is going to be 2.75. Hang on a second. There's no 4 in this number. I really don't know why I wrote it like that. So now it only has 4 decimal places. I thought that was weird that I took it out to an extra one. So it's actually just 2.75921005. So sorry about that. So when you round that to 4 decimal places, you get this. Okay, so notice here the slope is positive, which should make sense to us, right? Because as the price of eggs went up, typically the price of milk also went up. Okay, so let's see if we can use this to make some predictions. So if the price of eggs differs by 25 cents, I'm going to underline differs because that's kind of important, from 1 month to the next, by how much would you expect the price of milk to differ? So you could actually just make up some x values too, one that was 25 cents different than the other. But really all you need to focus on is that they're really just talking about the change. Okay, and the rate of change part of that formula is just the part that involves slope. It's just the B sub 1 times the x average. Okay, so a quicker way to do it, although you could again make up 2 prices and then figure out the price of milk for each of those prices of eggs and then compare them, but you also can do it this way. So you can just multiply by the rate of change and then times that change. Okay, so it's x bar, yeah, so this value, which is our B sub 1, right, and then times the change in x. Okay, and if you work that out, you get about 10 cents. Okay, so that would be the quicker way to do that one. And then lastly for this one, I want you to predict the price of milk in a month where the price of eggs is $1.95. Okay, it'll just be a prediction, but it'll be a pretty decent one because it has a strong correlation. So we're going to use our formula. So we're going to take 2.7592. We're just using the formula we have here. Okay, and we're going to add the slope and then times the price of eggs, which is $1.95. So it looks like the price of milk should be about $3.54 when the price of eggs is $1.95. Okay, so let's do maybe one problem where we just solve it all the way out. So this is going to be the last problem in this section, but it's going to be kind of a longer one. So I'm about to give you some values for the budget for some companies. That received government grants. Can't spell government. And we're going to compare the years 2006 and 2012. In other words, does the funding they get in 2012 have some correlation with the funding they got in 2006? Okay, that's a big complaint with politicians, the fact that they don't actually research who they're giving money to. They just look at last year's list and they're like, oh, we gave this organization $1 million last year, so let's give them $1 million this year too, instead of, I don't know, actually looking to see if they're worthy of that first. Crazy, right? Okay, so you are going to write out this table and you're going to pause the video. Okay, so notice we have 8 organizations and we're comparing in millions of dollars the amount they received in 2006 and 2012. So go ahead and write down that table. All right, so pause the video, but this is where the table went because I'm lazy that way, right? Actually, it's just that I already wrote it down and I don't want to do it again. So we need to find the 4 values. Okay, so we need to find the average. By the way, X is the 2006 numbers, so it would be the sum of the first column over 8. So this is 136.625. Okay, you might pause and check my numbers just to make sure that's what you get to. For the sum of the second column, the 2012 numbers, you would do that over 8. Remember, standard deviation's a little longer. So it's first amount minus the average squared plus second amount minus the average squared all the way through the 8 in the list and then over n minus 1. Okay, and of course take the square root of that because we don't want variance, we want standard deviation. So this works out to be 155.0096195. Let's do the same for the y's. So first y value minus that average. Make sure you switch to the second average. I've done that before and it's very sad when I get to the long end of my list and realize that I used the wrong mean. I have to start over. But if you work this out, you get 147.2504548. So I'm going to circle these 2. All right, so here's the part where, yes, it's tedious, okay, but yes, we do need to do it. So we have to find R, and remember R needs this full table, right? So we need the X's, the Y's, we need the X minus the averages of the X's over the standard deviations, and we need the same for the Y's, and then we need to multiply them together, okay? So pause the video, zoom in if you need to, but go ahead and write all of those digits down. Okay, you might also find the sum of the last column since that's what we're looking for in the end anyway. All right, so go back and pause if you didn't get that. But when we want R, we want 1 over n minus 1 times the sum of all the x minus x bars over standard deviations times the y minus y bars over those standard deviations, right? And so what we're going to get for R is 1 over 8 minus 1. The sum, if you worked it out, and I hope you did, the sum you should have gotten is that, which means the correlation coefficient is actually quite high. So it's even higher than some of the other ones we've been doing. So the closer it is to 1 or negative 1, remember, the stronger that correlation is. The closer you get to 0, it means it's very weak. It means they're probably not related at all. Okay, so now let's use that. So remember, b sub 1 is the R times standard deviation of y over standard deviation of x. So we'll use a squiggly equals because these are all rounded. So 0.995 sorry, hang on a second. This is the wrong answer. But if you work that out on your calculator, you might have seen that that wasn't the right answer. I was given the answer for one below. This is actually the R, even higher actually. Okay, so notice how close that is to 1, so make sure you change that. Sorry about that. So now I'm just putting the values that I found up top. And if you work that out, that's where I got the 0.945395551. And so now I can use that to find b sub 0. Remember, the formula for that is y average minus b sub 1 times x average. So it's 140.875 minus that 0.945395551 times the x average, which was this. And so this is what you get for the b sub 0. All right, so I did a lot of that work. So now let's see if I can answer some questions. So compute the least squares regression line, which I already pretty much did. I just need to write it out. So compute the least squares regression line for predicting the 2012 budget from the 2006 budget. Okay, they're highly related, which means if you got money in 2006, you're pretty likely to get money in 2012 also. Okay, probably even a little bit more. So here's the formula. We just need to pull these numbers in. So it's 11.7103 and then plus 0.9454x. Okay, notice we have a slope here, right, of 0.9454. So let's see if we can answer a couple more questions. So if two institutions have budgets that differ by $10 million in 2006, by how much would you expect their budgets to differ in the 2012 year? Okay, so this is another one of those differ problems I already asked you about. Okay, so it's really just asking about the change, which means all we really have to do is focus on the slope part of it. So we just actually need to take the slope times the change of 10. So it looks like they would change by about 9.454 million. Again, kind of like the milk and eggs example, if you wanted to, you could come up with two different amounts from 2006 that were $10 million apart and then plug them in and see how far the Y's are apart, but I think this is definitely quicker. And so lastly, I want you to predict the 2012 budget for an organization whose 2006 budget was $1 million. Actually, let's go $100 million. $1 million is too low. Nothing on the chart was $1 million, so. Okay. So we're trying to predict 2012 from 2006. Remember, X is 2006, Y is 2012. Okay. So it would be Y equals the 11.7103 plus the slope and then times 100. Okay, make sure that if you were writing this answer out that you remember that it's in millions of dollars, right? So it's 106.2503 million. So they're pretty sure they're going to get it, and they're actually going to get a raise. Okay. So I think I've said this before, I know I have, but I consider this stuff to be tedious, not hard. Okay, it's tedious to fill out the chart. There's no question about it. But if you could just keep your details straight, I don't really think the math is really that difficult. It's just there's a lot of numbers involved. Okay. One more thing to keep in mind is just because your R is high does not necessarily mean that you should abandon logic when you look at how related they are. Okay. So just in closing thought, there have been all kinds of studies on this, but the one that I saw that sticks out the most is they did a study on lemon exports in a country. So exports, you know, are goods that get sent out of the country. Okay, so how much lemons did they sell out of their country? Okay, versus how many car accidents that country had in any given year. Okay, and it found the correlation of those two things to be like 0.95. Okay, in other words, they were saying mathematically they're really, really related. Okay, but that's when I think logic has to take over, and you have to think, okay, even though the math shows that they have a correlation of 0.95, I really doubt that car accidents have anything to do with how many lemons we send across our borders, right? So keep that in mind. This is a statistical, mathematical calculation, but we also have to use reason, and we have to realize that some things don't have anything to do with each other regardless of what the math says. Okay. All right, so you should be able to do the homework for 4.2, and then you should be able to go ahead and start the quiz for Chapter 4 also.